All right, so for question number 1 here, we're looking for the height above the surface of the Earth, okay, not the orbital radius. We'll have to find that first and then find the height above the surface. But we need to find it for a satellite that's got an orbital period of 18 hours. All right, so we know the orbital period's 18 hours, but what do we need it in? We need the units to be seconds. I can't use Kepler here. Do I have the period of another object orbiting the Earth? Okay. Besides, that's not going to get me the distance above the Earth's surface anyway. So I need to first convert this number to seconds. So I'm going to take 18 and multiply it by 3600. Okay. And so we have 64,800 seconds. Okay. And that's the only thing that we're given, except that we know it's orbiting the Earth, so we know the Earth's mass is also part of this. Okay. So give them a mark for their given. / doing the conversion to seconds. Whether they did that or not doesn't matter. Okay, so it's a satellite. So we got FC equals FG. That's going to mean that we're going to need the substituted formula this time. So M is 4 pi squared R over T squared equals big G times the mass of the Earth times M over R squared. All right, so we already know mass of the satellite. Sorry, give them a mark for this step. Okay, we already know the mass of the satellite is going to cancel. All right, so we can take that off right away. We are trying to manipulate for R. We need to find radius and then subtract the Earth's radius from that, and we'll have the height above the surface. Okay, so we're going to multiply both sides by R squared, and that will give us R cubed. Okay, so that's going to come over here. We'll have R cubed. T squared is going to come up over here, and then 4 pi squared will end up on the bottom. Okay, and we're looking for R, not R cubed. So we'll have to cube root that. All right, so if they have this manipulation that R equals the cube root of big G times the mass of the Earth times T squared divided by 4 pi squared, right? You can have a mark for the manipulation for their third mark. Okay, or maybe they just went straight to plugging in the numbers. Okay, that's fine as well. So we would have 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 64,800 squared divided by 4 pi squared. Okay, and then our next step, okay, is to solve for what R is going to be. Okay, so we will have 6.67 e negative 11 times 5.98 to the 24. Whoop. Okay, times 64,800 squared. Okay, and we're going to divide that by 4 pi squared. Okay, so that's what we're getting, but that's, we have to cube root that yet, so we're going to go all right, so there's our orbital radius, 3.449 times 10 to the 7 meters. Okay, so if they've got something like that, 3.49 times 10 to the 7 meters, or maybe they had it all, as long as they have something there for radius calculated, okay, that can be their, sorry, that's not going to be their next mark. Okay, the height above the surface is going to be this number minus 6.37 times 10 to the 6. If they showed some number subtracting that number, okay, give them a mark because it's a method mark, whether they got this number right or not. Okay, subtracting that one, and then that'll give us our height. All right, so we should get 2.85 times, actually we only have two significant figures here, so it's going to be 2.9 times 10 to the 7. That's their fifth and final mark. Okay, that's as involved as a satellite motion problem could possibly get. Okay, it contained every single trick. You had to convert period. You had to use the substituted formula. You had to account for the fact that it wanted the altitude and not the radius. It had every single thing that could possibly not go your way in that question. All right, any questions on number 1? Okay, and for number 2, we have a space probe that's orbiting an asteroid. The orbital radius is 6.42 times 10 to the 5 meters. At this distance, the gravitational field strength is 1.5 times 10 to the negative 2 newtons per kilogram, which, as you learned the other day, is also the same as meters per second squared. It's the same thing. It's fine. Yeah, but they're technically the same thing, right? I don't know if I think I showed you guys this in the podcast, but I mean, a newton is a kilogram meter per second squared, right? Well, if you go newtons per kilogram, isn't that like this? The kilograms cancel, right? You got newton per kilogram, you got meters per second squared. They're exactly the same thing. Why they don't just make them exactly the same thing is beyond me. All right, so we know the gravitational field strength. So we know little g, 1.5 times 10 to the minus 2. We know the orbital radius, 6.42 times 10 to the 5 meters. Okay, and we are looking for the mass of the asteroid. Okay, so little g equals big G times the mass of the asteroid over the radius squared. So you can give them a mark for that and a mark for their givens. We're going to manipulate for the mass of the asteroid. So that's going to mean bringing r squared over to this side and then dividing by big G. Okay. Oh, whoops, sorry, that'll leave us with the mass of the asteroid. So if they have mass of the asteroid equals r squared times little g divided by big G, okay, give them a mark for that. Plugging in our numbers, so that's going to be 6.42 times 10 to the 5 squared times 1.5 times 10 to the minus 2 divided by 6.67 times 10 to the minus 11. That's their fourth mark, okay, for the numbers plugged in. And then our mass of the asteroid. All right, so mass of the asteroid is going to be 9.3 times 10 to the 19 kilograms. Fifth and final mark. Okay, give them a mark out of 10. Let them see it. And then on this desk right here in a nice neat pile, please.